Find the critical load in pounds. In this problem, two channel columns are subjected to a compression load PCR. The length of the columns and slenderness limit are provided. The columns have a pin-pin connection at each end, and the Young's modulus and yield stress of the steel are provided. The critical load in a column equals pi squared EA divided by the quantity LE over R squared, where E is the Young's modulus of the steel, A is the cross-sectional area of the column, LE is the effective length of the column, and R is the radius of gyration. From the problem statement, we already know the Young's modulus of the steel. The effective length of the column equals K times the length of the column, L. The length of the column equals 40 feet, and the variable K accounts for the end connections. For a pin-pin connection, the value of K is 1, which makes the effective length equal to 40 feet. After converting to inches, the effective length equals 480 inches. The cross-sectional area of the column, A, can be looked up for steel member C12 by 30, which equals 8.81 inches squared per member. And since there are two channel members, the area equals 17.62 inches squared. The last unknown variable is the radius of gyration, R, which equals the square root of the area moment of inertia, I, divided by the area, A. From earlier, we already know the cross-sectional area equals 17.62 inches squared. If we view the cross-section A prime of the column, the area moment of inertia, I, equals the smaller of the area moment of inertia about the x-axis and the y-axis. Since we know the member is a C12 by 30, we can look up the area moment of inertia about the y-axis, which equals 162 inches to the fourth power per member. Since there are two members, we'll use 324 inches to the fourth power for IY. To calculate IX, we'll use the parallel axis theorem and multiply the two members by the centroidal moment area of inertia of one member plus the area of one member times the distance squared. In this equation, the distance equals the length between the x-axis and the centroid of the member, measured in a direction perpendicular to the x-axis. Take note, this figure is not to scale. Knowing the member ID, we can look up x bar, which equals 0.674 inches, which makes D equal to 5.326 inches. We already know the cross-sectional area of one member equals 8.81 inches squared. And we can also look up the centroidal area moment of inertia, IC, for member C12 by 30, which equals 5.12 inches to the fourth power. This makes the area moment of inertia about the x-axis equal to 511 inches to the fourth power. The smaller of the two area moments of inertia is IY, which equals 324 inches to the fourth power. Now we can compute the radius of gyration, which equals 4.29 inches. We'll plug in 4.29 inches for R, as well as the other variables we already determined, and the critical load in the column equals 4.03 times 10 to the fifth pounds. Next, we'll make two checks. First, we'll make sure the axial deflection is elastic by confirming the axial stress in the steel does not exceed the yield stress of the steel Fy. After plugging in the appropriate values, indeed, the deflection is still in the elastic region, and our original equation assuming linear elasticity is valid. Next, we'll check the slenderness of the column, that it does not exceed the maximum allowable slenderness. After plugging in the variables, we know the chosen member is not too slender. When reviewing the possible solutions, the answer is D.